Hi, everyone. Today, what we're just going to walk through is going to be something that I've titled like a function assignment, but it's not really an assignment. Really, what it is you have a responsibility to know these functions listed on both sides of your page cold. That is, we're going to examine working through each one of these functions, and in the upcoming short while, we're going to end up going through and manipulating the graphs of these functions as well. So what I want to do is I want to go through relatively quickly the four types of functions, or I should say four of the types of functions that you're going to be responsible for working through this first unit. So we take a look at the instructions on the page. Listed below are examples of basic functions you'll be responsible for. Graph each of the following on their own sets of axes and summarize any unusual properties. We're going to kind of walk through that together. So the first thing that I want to draw your attention to is our first function, which is called an absolute value function. I am not making the assumption that anyone has any background with what absolute value references, but you could have come across it in your discussions on other topics in previous years. What these vertical bars represent around that X is the symbol of absolute value. And what absolute value references is the magnitude of something. So the short form for that is we don't really care what sign it is, we just care about the number. So we're looking at the magnitude of a value. We don't really care like on what side of the number line is it. So like another way to think about it is if all we care about is the exchange of something, then we don't really care whether somebody owes you 20 bucks or whether you owe somebody else 20 bucks. We just care that $20 is owed. So what we're examining then is the magnitude of something. So I'm just going to get rid of those red bars. We now understand what an absolute value symbol represents. How do we now operate with it? Well, if we were to deal with our table of values and sub in an x value of -2, and then I was to ask you, okay, with the number -2, what's the number? Or with the value -2, who cares about the sign? What's the number portion of that? Hopefully we can come in, well, it would just be a 2. If you were to sub in a -1, and now you had to find the absolute value of -1, that would just be 1. We don't care that it's negative. The other way that some people tend to think about an absolute value function is that it's always positive. My absolute value signs ask me to forget about the sign, and almost by default, forgetting about the sign means make it positive. So if I sub in a 0, then the number portion of 0 is 0, and if I'm subbing in positives, then I get no change. So what we could do is we could graph those points. And so if I was to go through and plot those points on relatively quickly, we should see that we get those points. And I think we shouldn't have to go through and extend our table, that those 5 points should give us enough feedback to be able to predict what the graph of that function would look like. Now it's just a matter of putting it on our grid. So hopefully we can see that if we were to sub in bigger negatives, it's just going to turn them into the positive value. And if we were to sub in positives, well, then it's just going to keep them as positives. And so as we go through and construct our graph, that graph that you have with arrows on the end to say that it goes on forever in those directions is going to represent your base absolute value function. So hopefully not too bad. Now I've also asked you right below to also name the domain and range of each of those functions, of this function. And so therefore we should be pretty good to say that my domain should be that x is anything. We could sub in any x value we want and find the absolute value of it. However, my range is going to tell me that if I sub in positives or negatives, the absolute value is going to turn it positive or 0. And so we come up with y has to be greater than or equal to 0. Yes, you can tack on that disclaimer or that restriction to also say that y is any real number on top of it, but you don't have to show that. we'll make the assumption that we're always talking about real numbers anyway. Now, we also have the option to go through and you can write it in that set notation, or if you want to choose interval notation, I'm just going to put our or down here, feel free to express it in that form as well. Remember, I will never mandate, I'll never make you use a certain form, but we have to make sure that we can interpret both forms. Okay, hopefully that first base function went okay. Let's jump into the bottom of the page. Okay, so what we see now is our square root function, and everybody should be familiar with what a square root operation looks like. Okay, we should be able to also go through and pretty quickly come up with our table of values. So for us to be able to work our way through, we should be able to sub in a 0 pretty quickly. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. And square root of 9 is 3. Making that substitution allows us to plot 0, 0, 1, 1, 4, 2, and 9, 3 doesn't fit on our grid, but we know roughly where the location of that would be. It helps us to then draw on the nature of that curve. We can now connect that with a smooth curve. We've got an arrow on in one end, because we know that that graph would go on forever in that direction. However, we should be pretty good to be able to realize that if I was to try to sub in, for instance, an x value of -1, I cannot take the square root of a negative value, and so my function would not exist anywhere over here left of the y-axis. So we have our red graph. There is our base function. Okay, we should be pretty good to either look at the equation or look at the graph and determine our domain and range. So our domain in this case, I can only sub in x values that are greater than or equal to 0. And my range is going to be only y values that are greater than or equal to 0. Now, I do want to just come back and maybe hit one key point for us. That I could see some people going, but wait a sec. When I take the square root, I get two solutions. And I want to make sure that we're good why in this case we do not. Just keep in mind that that equation has the square root operation in there. And when you look in front of that square root, you'll notice you don't see an operation. That tells us that it's a positive. So when I take the square root of that positive value, then it only gives me positive solutions. I'm actually finding what's called like the principal root. However, where this differs is that if I gave you the equation y squared equals x, and you wanted to get the y all by itself, then you may say, well, I'm going to choose to do the square root operation. That is, I'm putting that operation in there. And when I choose to take the square root of something, then there could be a positive or a negative case. So let's make sure that we don't confuse that. The operation is already there. We can see the sign that it is. Now, on the bottom of that page, you're also going to notice that I've introduced kind of this idea of key points. The reason why I want you to be focused with key points is when I said that we're going to start to use these functions moving forward, I want you to be able to graph each one of these functions in like 15 seconds. That is, we're going to know it well enough that if I asked you what your base square root function looks like, you should be able to put that quick picture on the right down in under 15 seconds. In order to do that, we want to plot a few key points, and we want to have a few key points already known. You see those key points on your graph right now. Let's make sure that we're good that a square root function starts at 0, 0, and then passes through 1, 1, and 4, 2. If we know those key points, then I think you're on a good path to being able to use that function well. Okay, let's turn over onto the back of the page. Things are going to step up a little bit. Okay, what we have now is our equation y equals 1 over x. And I am going to put forward the idea that I think this is probably going to be the most complex function that you'll be responsible for this year. This is called a rational function. I'm hoping we can recognize that rational is just another way of saying fraction, but it's kind of a different reason for why it's rational. Yes, there's a fraction in there, but it's more about where the variable is. And I want you to notice that within that function, we have our variable on the denominator. That's what makes it a rational function. Now, rational functions also go by some other names. That is, we can refer to that as a hyperbola. And so just like in grade 10, you guys had your parabola. Well, now we have a hyperbola. Or another generic term for that would be a reciprocal function. And you may end up working your way through and thinking about it as a reciprocal function from the idea that reciprocal tends to us to mean like, you flip it. Like if we're dividing fractions, we multiply by the reciprocal. That could be a reciprocal graph to y equals x. The way we're going to think about it, we're going to think about that as a hyperbola. That is a rational function. And we should be able to pretty quickly go through and come up with our table. So if I blindly just kind of subbed in all those x values, well, if I sub in a -2, then I'm going to get -1/2. If I sub in a -1, then I'm going to get -1. If I sub in 0, we should be good that is undefined. That I can't take 1 and break it up into 0 groups. That means that function is undefined at that value. I sub in 1 and I get 1 divided by 1, and I sub in 2 and I get 1/2. So what does that mean graphically? Well, it means that I have a point at -2 and -1/2. I'll do my best to estimate halfway. At -1, -1, at 1, 1, and at 2, 1/2. And my undefined tells me that I cannot have a point that has an x value of 0. So we build our table like that, and I don't think we have enough points to be able to confidently connect those. That is, I don't think we can just go, oh, okay, I can see the pattern in the function. I think what we probably want to do is maybe extend our table a little more. That I might argue if we added in 1 more x value into that table, we may have enough to see the nature of the curve. The x value I'm talking about is, why don't we sub in an x value of 1/2? If we were to sub in that x value of 1/2, then we're going to get 1 over 1/2. And I understand that we don't like fractions within fractions, but just take a look and notice that I drew down a dominant fraction line. One of my fraction lines is significantly larger than the other. So if I was to calculate 1 divided by 1/2, we should be good to multiply by the reciprocal, or flip and multiply. And that gets me a y value of 2. That if I now plotted the point 1/2, 2, and again, I will do my best to estimate that 1/2, then I think we could be able to see the trend in the graph. Okay, let's take a look at what would happen. I'm not going to do it, I'm just going to think about it, about subbing in an x value of 3, or 5, or 10. Notice we're going to get 1 over 3, or 1 over 5, or 1 over 10. That's going to tell us that we're going to get ever increasingly smaller values. But if we do the same with the blue points, and instead we subbed in like 1/3, 1/5, 1/10, then when I take 1 divided by those values, I end up getting bigger values. And so if I went to connect all of those points, then I should get something like this. We should be comfortable to say that you could continue subbing in huge x values. However, we should notice that there is no way that you are ever going to get a y value of 0. The only way that my equation, which is a fraction, could ever equal 0 is if the top equals 0. The only way I can divide and get a 0 is if I started with 0. That is, I have to have 0 divided by some number. And I just want us to notice the top of my fraction will never equal 0 because there's no variable up there. It's always just 1. And so we should see that if you started to sub in larger and larger x values, you're always going to get 1 of something. So you're going to take 1 and you're going to start dividing it up into bigger things. You're going to take 1, you're going to divide it by 100. You're going to take 1 divided by 1,000,000. You're going to take 1 divided by 1,000,000,000. You're always going to have like at least a bit. And so we're going to see that portion, and I'm just going to highlight it here. We're going to see this portion of our graph always equals something. We're never going to get to 0. And since we never get to 0, that means we never hit the x-axis. Okay, if we alternate that a little bit, then we should also be good that we're never going to hit the y-axis. Now, we know that we don't have a point on the y-axis because when I sub in 0, I get an undefined. But we should also see that we could continue that trend with our blue points and continue to sub in smaller and smaller and smaller values and get a function value that is huge. Okay, what we're actually going to have then is that exact same shape that you see on your graph, but we should all be good that that same thing will happen down in quadrant 3. That if I was to then go and just alter my table, and so instead I'm going to imagine subbing in like -1/2. Well, -1/2 subbed in is going to give me a -2. So -1/2, -2, and again, I'll do my best to estimate. We should see the same trend in our graph as we go down. But then if I was to sub in larger negatives, we should see that we're going to have the exact same thing. We're always going to have a bit. It's just that those bits are going to be negative. Okay, that is almost our graph. At the very least, that represents the curve portion of our function. However, we have 2 other features that we need to put on. What I need you to do is to take a straight edge, and we are going to put a dotted line just to one side of our y-axis. We put it to one side of it so we can see it. But really what that dotted line represents is a property that really exists on the axis. So that means we need to label it with the proper equation. Notice my y-axis would have the equation x equals 0 because everywhere along my y-axis, my x-coordinate is 0. That dotted line represents a line that my curve is going to approach but not touch. And that has a very special name. That's called an asymptote. I'd like you to just get down the definition for that asymptote. All it is a line that a curve approaches but, and please put down, does not touch. And so the way that we can show that, well, my curve's going to get as so close to my y-axis, but to account for human error, we put on our asymptote to show that that is a property of that function. Okay, you might also notice that there's another asymptote on that graph. I said we were missing two features. Here is the second one. I'm hoping that we can see we would also have an asymptote along our x-axis. So I put my dotted line to show that it's not part of my curve. I put it slightly on one side of the axis, but I need to tell my reader that it really exists on the x-axis. I'm only putting it slightly off so we can see it. So I need to label my equation, and we should be good that our x-axis has the equation y equals 0. Again, because everything along the x-axis has a y coordinate of 0. So what you now have on your grid, that is the base graph of our hyperbola. And we need to know that graph cold. So to help us out, let's look at a couple key features. What is the domain of that graph? Well, we could say that x is anything but the one value that we can't sub in. And therefore, x cannot equal 0. Now, in terms of form and expectation in our course, again, you wouldn't have to write the x is an element of the real numbers notation. If all you did was state x does not equal 0, then we'll make the assumption that it can be anything else. So take a look at your range. What are your y values for that function? Notice my y values could be anything except 0, because I have an asymptote at y equals 0. So there is our domain and our range. We know our curve exists everywhere except for those values. What are the key points that we should use in this case? Well, for us to get down our key points, I would hope that we use that 1, 1 and the opposite point on the other branch of that function. So I'm going to use 1, 1 on the one branch, and I'm going to use -1, -1 on the other branch. And then what we do is we use the nature of the curve, knowing that it represents a branch that approaches its asymptotes to give us the shape of that graph. Okay, I think by taking a look at that one, you can maybe see why I would argue that our hyperbola, our y equals 1 over x, is probably going to be the ugliest function that we work with. Okay, let's almost like take a step back now and finish off the last one. Okay, so what we have then is our exponential function, and I think we should be pretty quick to fill in that table. At the very least, when we sub in, let's look at our exponent of 1, then 2 to the exponent 1 is 2, 2 to the exponent 2 is 4. Those two should have been automatic. However, we do have to think back maybe. When I sub in my 0, 2 to the exponent 0 is 1. That's a property that we should have discussed in grade 9. That any base, as long as it's not 0, put to an exponent of 0 gives us 1. And maybe we needed a little bit of review dealing with our negative exponents. So when I make that substitution of 2 to the exponent -1 or 2 to the exponent -2, I would hope that we would take a look at that and realize that neither of those makes sense. Remember what exponents mean. It means repeated multiplication. That if I was to give you something like 2 cubed, we should be good on what 2 cubed means, but we should also be good on what it means with proper vocabulary. Sometimes we fall into a trap, and we've been allowed to fall into that trap by the way that we word things in the past. That I have a feeling some people would tell me, well, 2 cubed means 2 multiplied by itself 3 times. And I'm going to follow exactly what that wording means. 2 multiplied by itself 3 times. Well, that's 2 multiplied by itself 3 times. And so if you then multiplied all that stuff, very quickly you should be able to tell me that's not what 2 cubed means. But that's what my wording tells me to do. So I hope that we can see that our wording is actually misleading. Yeah, it was fine for when we had something basic like 2 cubed, but maybe it causes us some problems when we have the green. Really what an exponent means is you have that number of bases. So when I have an exponent of 3 on a base of 2, then that tells me that I have 3 2s. That is my number of bases. And that an exponent says separate them by multiply. That's what an exponent means. So if I get rid of that blue, let's take a look at our green and realize that that doesn't make sense. Like my second power, 2 to the negative 2, is going to tell me write down the base 2 negative 2 times. And I hope we can see that that doesn't make sense, let alone writing down 2 negative once. And so, because those negative exponents don't make sense, we need to change them into positive exponents. And hopefully we remember a property that says, if I want to change the sign of my exponent, I can move my power across its fraction line. And so if I move that 2 to the negative 2 across its fraction line, of which we know every term has a fraction line, then I get 1 over 2 to the exponent of positive 2. Well, that's going to get me my 1 over 4, and that's pretty automatic. And so pretty quickly then, we should be good to say that that would be a 1/2. And we come in with that table. Okay, we should be good to plot those points relatively quickly. Again, I'm doing my best to estimate. Negative 2, and I'm up a quarter of the way. Negative 1, and I'm up halfway. 0, I'm at 1. 1, I'm at 2. 2, I'm at 4. And if we plot those points, then we should feel pretty confident about making this curve go through these points and then become steep. And that graph is going to extend on in that direction forever, getting really steep. But then as my graph comes to the left of the y-axis, I'm going to a half, to then a quarter. And if we see the trend in that graph, I would then be going to 1/8, 1/16, 1/32. Yikes. It's really even hard to draw that graph on. And I'm hoping that just given what I just did of reading out those values of 1/16 and 1/32 and 1/64 and 1/128 and so on, we should see that we are always going to have 1 of some power of 2. And what's the only way to make a fraction equal to 0? If the top equals 0. And we notice we have the same instance as what we just had with our hyperbola. That exponential function will never have a value of 0 because there is no exponent that I could ever put on 2 that gives me 0. If I put on positive exponents, they're going to give me huge values as I go. If I put on 0, then it gives me 1. And if I put on negative exponents, it just gives me really small values. So we might be able to predict then what we have along our x-axis. Yep, we got our good old asymptote. So we're all going to put on our dotted line. And it's like we're old pros with asymptotes now. Label it. That graph will never get to a y value of 0, but it's going to approach it. And so we should be good to be able to hit out our domain and range. So our domain, I can sub in any x value I want, and I can calculate it. In other words, I can put any exponent on 2. However, when I go to calculate that power, I'm always going to get a positive value. Notice it doesn't equal 0. It's always above the x-axis. So my y value always has to be greater than 0. What are my key points in this one? Well, if we get really good at stating 0, 1, my y-intercept of 1 always has to be 1. Because when I put an exponent of 0 on 2, that gives me 1. And then what I do is I just use the nature of the curve again. And really what that is use what you know about powers. As I put big positive exponents on, then I'm going to get a huge value, so it becomes really steep. And then when I put negatives on, I'm going to get really small values, so it becomes very flat. This y-intercept is actually going to act for us as like a hard turn. That's where we change between being very, very steep versus very, very flat. Okay, there are our 4 functions, or 4 of our functions. We throw in our parabola from last year, and we have a series of functions that we should be good to start working through some changes to start affecting the graphs of. Okay, your job is to walk in next time, and I'm going to give you a little bit, but you want to know those functions cold. Okay, good luck.